Okay, we should be live now.
Yeah, okay.
Give me a second. Yes. Yeah, we're live now. Yeah, so for everyone else, if you got my email, you know, I cannot give the lecture at the usual time because my kid is sick and my partner is also sick. Complicated day. But if there's a time during the nap period, which is like from 1 to 3, where it's especially good for you and you want to watch it live, let me know. You can just write in the chat now. If not, then I'll do it at whenever I can. And you watch it later on YouTube. Yeah, 1 to 2 works for me. Is this okay for the others as well? Yeah, okay, so then we do it at 1 p.m. Okay, thank you so much. I'll leave this one.
Great, good. And now I think okay, good, great. So hello everyone, welcome on this new paradigm. I hope, yeah, we will find a good strategy to sort it out and still have a nice exercise class. Yeah, I'm sorry. My office or my home office was occupied by bikes at home, so I tried to change the angle. It was not possible. They are in the background. I hope they are not too distracting. So please interact with me. Just write in the chat for every possible thing, especially we are a small group, so I can really stop wherever you want. And yeah, I have the chat on my right. It should be always possible to read me for me. Ask any question and also tell any wish you have. Today we are focusing on spin systems because we have an exercise sheet which with some technical issues it shouldn't be now uploaded. So as you are probably in front of your computer, you can open it. It's all about spins. And spin is something very exciting because we go one step forward from just the qubit paradigm. And actually, if you think about experimental physics, but also like materials and everything else, it's more complicated system. We have multiple qubits or multiple spins, and we look at their properties. And I will also very quickly show you an example of my research where 1 month ago I had to calculate a ground state and exactly found out a singlet and a triplet, which is what you saw in the lecture. So what are the ingredients? Because we always need ingredients or to cook something. The first of one are the operator, Sx, Sy, Sz, with their commutation relation, which are very important properties. And for the spin half operator, spin half system, these operators are known. For other spin system, these operators have to be kind of calculated or guessed. And one of the exercises of this week is calculate this operator for the spin 1 system. What do we have? Otherwise, we have the S2 operator, which is defined like this, and is also particularly nice because of some commutation relation with the Sx, Sy, and Sz operator. And we have other operator which are the ladder operator. And this is also something you discussed it in the lecture. And this is S plus equal Sx plus Sy. S minus, this was the definition. And from this, it follows, this is equivalent that you can write the Sx and Sy operator in this way. And Sy, S plus minus, S minus. And this is, so showing this, is exercise 1A of this week. Why am I writing this now? Because we will see later how this has to kind of be used for the exercise, following exercise. I think it's exercise 3. Can I repeat? Anything is unclear, write, raise your voice, scream. I'm here to answer your question. So the plan of today's lecture is a recapitulation of the definitions, which here I did it just quickly for the operator. And we in particular look in the lecture, you saw the spin 1/2 case. What does happen if we look at a spin 1 system? And for this, we combine so the recapitulation of the definition and this, and we look here. Yeah, actually, this with a color is good. Spin 1/2 and spin 1. So for spin 1/2, we have the matrix Sx, which is given by this. Or like the operator, we could write the operator Sx, which is represented by this matrix in the up-down basis. A basis of an operator is always very important. Divided by 2 of 1, 0, 0, minus 1. And here we see that in the up-down basis, the Sz operator is diagonal. This means that the state up and down are eigenstates of this operator. And if we calculate the S2 operator with the definition so before, we observe a similar, like same behavior. We will get a diagonal operator. This means the up and down states are eigenstates of this operator. Now, what about the spin 1 system? Let me go a little bit here. We have a basis which we define as minus 1, 0, and 1. And these, like in here, we had the basis up and down. We could write this, but it's not very, like I put it in as, sorry, this is a down. This we could put it as a down. The 0, we could put it something like this and up. But this is quite a terrible notation. So we stick, or most of the community sticks to this basis minus 1, 1, 0. With the up-down basis, is similar to the computational basis 0, 1. Exactly. Here, for a qubit, but also in the computational basis, we wrote this up is 0 and down is 1. Exactly. Yeah, very good point. For spin, it's very common to write to use arrows. For spin 1/2, for spin 1, not really. Yeah, but of course you're very free to do it. Why am I telling you this? Because in the exercise sheet we use this notation, this one. Okay, 1 minus 1, 0, 1. And what do we have with this? We write the Sz operator. We kind of decide to have it similar properties to what we to the spin 1/2 case. And here we have minus 1 Sz of 0 of the 0 state 0, and Sz of 1 is equal H1. So these are the, let me choose another color. This is the eigen value, and these also, or these are the 3 eigenvalues. in the SZ case, for the spin half system, you had an eigenvalue of h bar divided by 2 for spin half, spin up, and minus h bar divided by 2 for spin down. So the SZ operator tells you in which direction or how does the spin point. If we have this 0 spin, the SZ operator returns 0. If we have the down spins, it returns minus h bar. The h bar is kind of a prefactor. The direction of the spin is like the number, the integer, not integer, because in the spin half case, it's 1/2. So the number, it multiplies the h bar. Anything is unclear, please tell. Now, what is the question? Is what do we have for the spin 1 case here? Sx, what are the Sx operator and the Sy operator? And this is exercise 2 of this, exercise 2, exactly, of this theory. Sorry, exercise 3, exercise 3a. This is great. I wrote it down wrongly, and that's why I was confused. Now, how we do proceed in such a case? There is kind of a cooking recipe. The key ingredients are the properties is that SZ is diagonal in the basis -1, 0, and 1. And this is the product basis. You discussed this also in the lecture for the spin half case. The up and down is the product basis of the system. And now we have exactly this one. Okay, so it's kind of exactly taking one particle or no superposition, no entanglement, the product basis of pure states. And so what does it tell me now? I want to, here actually we also have to find SZ. I have these properties. This means that if I calculate SZ as a matrix like this, SZ times 1, 0, 0, this must be minus h bar 1, 0, 0. And this is the vector representation of the -1 state. Okay. So now I have this requirement. This means that if I write the SZ matrix, the SZ operator as a matrix, I will have some coefficients here, which multiply 1, 0, 0. And what happens here, now I don't care, because they will be just multiplied by 0. But what I care is that I know that this is minus h bar for 1, 0, 0. Okay? And similarly, and okay, yeah, from here I multiply h by 1, b by 0, c by 0. This means that h is 1, b is 0, and c is 0. Okay, this is also b and c follows also because, yeah, exactly, sorry. B and c are ignored because it's diagonal. This actually, yeah, it makes it very easier here. We have this property here. SZ is diagonal in the basis, so I can just follow these two follow from the previous fact. Thank you for the, yeah. Now I can also do exactly the same for the next vector. So now I will have that as z times 0, 1, 0 for the 0 vector is equal 0. And here I will have again, now I have one h bar. Here I have an h bar 0, 0 calculated before. And here I will have again an unknown number and then something I don't care, 0, 1, 0. And this must give 0. This means that here we have, and here h equal 0. Okay, and this is like how to find out matrix, the matrix representation of an operator with known properties. We know that is diagonal in this basis, therefore we only have to calculate 3 coefficients. And with these, we found the first operator. Now about Sx and Sz, we don't know anything about them. Okay, so this, then we have Sz is calculated also with the next step, which we are not doing now. Now the question is Sx and Sy operator. And how can we determine them? We have the definition of the S plus operator, h of square root of s plus 1 minus m plus 1 of m plus 1 m. And here s minus is equal sum of m of s square root of s plus 1 minus m minus 1 m minus 1 m. Okay, and the square root, no, it's actually correct. And here this is the product basis, because it has defined m. Now, how can we use this to find out Sx and Sy? We know from exercise 1a and b that if we calculate S plus and S minus, as here, we can determine Sx and Sy. And we have a bracket, the definition for the S plus and S minus operator, but not for the Sx and Sy. Therefore, we proceed with this. And so with this, with these definitions, we can calculate the matrix representation of S plus and S minus. And how do I calculate our matrix representation? Quick recap. So matrix representation of operator. We have that if I have an operator here, and in the psi I basis, any matrix representation is with respect to a basis. I will write this as, so the first element here will be the expectation value of the operator of the psi 1 vector. And then here I will have this is not an expectation value anymore, but like a overlap of these two vectors applied with the operator. Here I have a hat, which doesn't make sense. O psi 3 and so on. here I will have psi2 or psi1, psi2 or psi2 and no hat, and so on, and the rest for all of the element of this matrix. And many cases you write O, E, J, like to tell this is the element of the matrix on the each row and j column as psi I or psi j. Okay. So now what we are doing, we apply this to calculate the S plus and S minus. S plus and S minus in this way. How? For example, S plus of 1, 1, I'll write it now. So this would be the element here. This is given me as the minus 1. Yeah, and using basis again, using basis minus 1. Oh, it is in cat form. Oh, what is doing? Here. Minus 1, 0, and 1 as defined before. So this will be calculated like this. And what if I input the forms seen before, I will have yeah, for spin 1, I have S equal 1. This is what we saw in the lecture. Okay, this is spin 1/2. We will have S equal 1/2, which is to input in this formula here. And then I have here, I will have then the square root of 1 per 1 plus 1 minus minus 1, which is m per minus 1 plus 1 times minus 1 m plus 1, and then here m and minus 1. So here we see that this is 0, sorry, square root of 2. And here we see that for any combination, if this is unequal 0, this means that m will be minus 1, and this will give then 0. If m equal minus 1, this will return 0. Sorry, I just realized this will return 0. If here we want a non-zero element, we need m which is equal minus 2, which doesn't exist in a spin system. Or anyway, one of these two terms must be 0. So this element is 0. So if I write my S plus operator in a matrix representation, I know now that this element is 0. Should the minus 1 and minus m and n plus 1 so sorry, so should the minus 1 and minus yeah, this is correct. Yeah, thank you very much. This is it doesn't change anything, but yeah, thank you for the comment. Here we have m and m plus 1. Thank you very much. Yeah, anyway, it's 0 is exactly what we get here. Now what we, for example, here, let's go for this. So this is our S21. What is S21 here? S21, will be given by 0 s plus, so my 0 state and -1. And here we will have h bar sum over m, and then again the square root of 2 minus m plus 1 times m. And here we will then have 0, m plus 1, and m minus 1. So here, this is a bracket. Now we see that for m equal -1, this is 1, okay? And -1 plus 1 gives 0. This means this gives 1. For any other value, of course, we will have 0, because just if we see at this term here, no other value can give me, no other m can give me a non-zero element. So here I will have that S21 is equal h bar square root over 2 minus -1 per -1 plus 1. And this is all. So this will be h bar square root of 2. And now what do? We take this element here and we go up. So we can put it in this matrix here and have h bar square root of 2. And for the rest, we proceed exactly in the same way. And for here we'll have a s plus. For s minus, for the s minus operator, exactly the same. And once we have this, we can go back to our definitions here. And if we have a matrix form, then calculate the matrix representation of the Sx and Sy operator. We just simply add two matrices or subtract them. So nothing very complicated. And yeah, this is just, after this, you will have defined the spin matrices of a spin 1 system. Then you will see that, for example, in the rest of the exercise 3, actually what we use is the definition of, in this way, Bragg and Ket definition, because as we also saw in the rest of the system, it's way easier to multiply Bragg and Ket than find out the matrix representation and calculate the vectors and so on. Then it's also asked to calculate the S2 operator. There you can just do it with the Sx square plus Sy square plus Sz square. And this is exactly the way also one can do it for another spin system, spin 2 or something like this, even if we will find out that actually only particles with spin f and spin, or yeah, no, actually, yeah, it exists any possible case, but usually we see these two because it's the particles which are observed in nature most of the time. Great. Then, yeah, another comment is attention. So operators are not necessary Hermitian. Why am I telling you this? Because Hamiltonian, we know that this is equal the transport conjugate, which we write like this. This means that if we calculate all of these elements of the upper diagonal of H, then H, so a full H is known. Because I just take this element, take the complex conjugate, and I insert it in the transpose place. So this is because Aij is equal Hji complex conjugate, if we write it this in a matrix representation. For operators, it's not that case. You have to compute, in this case, all of the 9 elements. Great. Then we will now move to the adding spin. Great. Yeah. I'll just start a new page. And in the lecture, you saw the case of adding 2 spin 1/2 particle. The exercise is adding 2 spin 1 particles, and this is actually from the exercise 3B onwards, and it's actually quite guided. So we will more look at the cooking recipe and what you did for the spin 1/2 particle, such that you can really exercise it and try it on your own. I don't think it's too difficult. There are also in some cases the results, so you have to try to recover these results. And if you're blocked at some point, you can write on the Moodle or write me an email. And with this, we also relook at the motivations of this definition of the Hilbert space and composing different spin, because I always find it a bit, not very intuitive and quite like there are a lot of assumptions and definitions. So we try to recapitulate it. And if you have any question, just raise your voice. So the idea is that the S2 operator is Hermitian. This means that its eigenvectors span the whole Hilbert space. And this makes it particularly useful because then we have a basis which has similar properties. It has the same, it has defined eigenvalues of the S2 operators, which gives us information about the spin configuration of a state. So the idea is that from here, we choose the eigenbasis. S2 psi, so that this returns me f of psi. And this h bar here, we insert it because it's a constant. We know that the Sx and Sy and Sz matrices have this constant, so the square of these matrices will have a h bar in front, and then we just keep it apart and focus more on the function here, which is way more interesting. So we write then h as the span of Hilbert space, and I will now focus here. Span of psi h, so that S2 psi is equal h to f s psi. So this is exactly what we just defined here. Why are we doing this here? Why does this pen doesn't work anymore? Let's try like this. Oh, otherwise I don't know what I can do. No, it's correct. Let's try to erase. The erasing works. Ah, now it works. Great. Good. Good. Sorry. Technical issues as usual. Why this? because if an operator is Hermitian, we know that its eigenvectors span the full Hilbert space of this, where this operator lies, but it doesn't tell you that there is no degeneracy. So it can be for a psi prime unequal psi, it can be that both of them have the same eigenvalue, psi prime, and S2 psi is equal h squared f of s psi. So this is degeneracy. So this sum accounts exactly for the cases in which we have degeneracy, and we kind of group each other all of the states. And as we will see later, this is also a very important step for the calculation. Now we know about something else about our operators, which is, so property 1 is this, that S2 is Hermitian. Property 2 is that S2 and SZ operator, they commute. This means that S2 and the SZ operator share an eigenbasis. And these are properties we saw, I think, at the very beginning and come in handy now again and through the whole story of quantum mechanics. So how can we use this property to write again our basis, or to see how our Hilbert space behaves? We write HS, so we decompose each of the subspace here with the same eigenvalue of the S2 operator. And we will write here as a span of states of our full Hilbert space, so that this state is an eigenvector of the SZ operator with eigenvalue Fs, and SZ of psi is also an eigenvector of the SZ operator with eigenvalue Hn. And why this? And it can be that for a state with eigenvalue h bar f of s of the S2 operator, as that has degeneracy in its eigenvalue. So it exists more than one state which has exactly this eigenvalue of the S2 operator, but multiple for the SZ. What does it follow from here? We have that, no, this is not possible. Why is this pen giving me troubles? Okay, no, so therefore we can write HS as a composition of HSM, and this tells you that the full Hilbert space is a composition over spin and M value, which we will see afterwards what they are, of these subspaces H, S, and M. So we look at the eigenvalues of the S square operator as SZ operator to just decompose our full Hilbert space, which can be very complicated, and write it as like a combination of sub-Hilbert spaces, which in many cases they don't really talk to each other. And what is very important, each of these sub-Hilbert space has similar properties or has the same spin property. And then, yeah, a small comment for simplicity. No, it's not possible. What's let me show. The pen is charged. Or what is the pen making? It doesn't tell me how charged it is. I charged this morning. Let me wait 2 seconds. Yeah, and then in 2 minutes we have a break, and then I try to recharge it, but I don't think that's the issue. So for simplicity, f of s is equal s of s plus 1. So these we inserted in each of these part here and here and so on. Now, why is this important? So we know that for one particle, we write the product basis. And we use the notation many times S and M. Okay. And here, this tell me the spin character, so to say. And this tells me the spin value. And I will come in 2 seconds. If we have the up state, for example, for spin 1/2 particle, the up state will be 1/2, of course, because it's spin 1/2 particle. And then the spin value, which is 1/2, it points up. The down state, we write it as 1/2 and minus 1/2. And these are eigenstates of Sz and S square. Now, for multiple particles, we will have that here Sm will be kind of the S1 plus N for and M1. So this is kind of the sum of the spin character. So the spin character, it's like the total spin possible. And this is like the total spin value. So if we have a multiple particle, each of this particle has a spin value, we multiply all of the spin and we get the total spin. But this is not, in general, not an eigenstate of the S2 operator. So this we have to calculate. As we want to decompose our Hilbert space in sub-Hilbert spaces with the same characteristic regarding the spin, we have to figure out how to do it. And this is the notation of adding spins. Now it's time for a break. I don't know, what do you prefer as we are online? Do you prefer to do a 5-minute break, 10-minute break. Just tell me your preference if you have any. If no one tells anything, I will stay with the 10 minutes break. Okay, then let's meet in 10 minutes again. Great, good. And perfect. Thank you very much for the reaction. So let's meet in 10 minutes again, and I'll try to fix the problem with my pen. And if you have any question, I'm here, of course. I will stay online. It's my, it, oh yeah, thank you. Yeah, yeah, of course, this is a minus. I also, here we have the minus, yeah, then H is minus. Thank you very much. Yeah. Sorry for this, I don't know why. Very simple calculations, then when I'm in front of the camera. Great, I think we can restart. So one thing I just noticed, actually, I wrote it as like S1, as N, M1 and N, but this is something actually, yeah, we write it some only in very special cases. So the very correct and elegant and actually notation is also the one we should use is with product, or we have multiple particle and each particle has a S and M value. For the spin 1/2 system, we can also use the other notation. For the spin 1, we have like 1 and -1 and 0. So we should really write like if we have, sorry, this is the basis. 1, -1 and 0. So if we write, for example, it's for one particle, we will have, for example, the state 1 -1, and this is S and this is M. For two particles in a spin up system, we would write, so spin 1/2, we would write maybe up and down. And this is clear that this is my first spin and this is like my second spin. But for spin 1, we would, for example, write up, like up and down, like this. And the two here is a problem. Okay, as we don't use the arrow, we have, therefore, so this notation don't use, please. Use really one tensor product -1. And this means first particle, and this means second. And these will be then equal something. So if eigenstate of the S2 operator, we write something like SM. Also for two particles, also for the two particles. Yes, so is it suitable to omit the tensor product symbol but still have two distinct cats? Yes, absolutely. Is the tensor product, I did it in the exercise sheet. If you write like this, 1 -1, this is also very clear what you mean. Yeah. Great, good. Then it was twice the same question, so I think everything is okay. Yeah, this is important just for exercise 3. And now a small comment about, yeah, why is this S2 operator and the basis? So the product basis in, for example, in up and down, so for spin 1/2, we have the two vectors, and then we can write for two particles, we will have up, up. Now I use what you suggested, which is makes everything faster. Down, up, down, up, and down, down. So this is my product basis. For spin 1 particle, the idea is the same, or we have 1 -1 1, 0, minus 1. So we will have 1, 1, and so on. And we write this, so in general, as the tensor product over J of Sj Mj. Because all of these are equal on Sm. Because for one particle, these are exactly the eigenstate of the S2 operator. So this is the product basis of n particles. Now, so for an operator of S2, we define it as Sm. So Sm global. Sm global, we can rewrite it in the product base, which is the most intuitive one we know. It's the one we always use because there we know, okay, the first particle is in up, the second is in down, and so on. So to rewrite it in this basis, we use the identity operator, and this you also saw in the lecture. But there is an exercise, the 1b, so that's why I'm just showing here. Why this? Because this is the basis that we want to use. This is an identity, so we didn't change anything. This is again global. So this is my coefficient. So basis coefficients, which are called the Clebsch-Gordon coefficients. And this is exactly what we want to calculate when we add spin particles. And this is also what you did for the spin 1/2 case. So for the for exercise 1b, you have to show that now I'll tell you, you can look at it, and that to show that this product, that the superposition of a product state and a state which is eigenstate of the S2 operator is 0 unless m is equal, so the value of m is the sum over mj. Is this sum part of the identities? Yes, great. Yeah, absolutely. Thank you for that. I might make it a bit clearer. This is our identity, or we have to sum over all of the possible thing to have the value. Thank you. And for this, use the decomposition here. Use decomposition just before. And also, like, if we have, if Sm, so if we have a state is equal a sum over psi I, then all psi I must be of, like the sum of the spin must be of m. So if we have multiple particles, we sum the spin of all of them, it must be of m, as it's an eigenstate of the SZ operator. Maybe you can think a little bit about it when you do the exercise, is also a part of it. So this is a property of the Clebsch-Gordon coefficient, which helps calculating Clebsch-Gordon coefficients or checking that your Clebsch-Gordon coefficients are correct. But how do we calculate them in like explicitly? So the idea is that so calculation, so composing space system. And this is exactly like the cooking recipe we are seeing now. So the idea is that we have H total is the sum over sub-Hilbert spaces with same S and M. So this is like aim. And to calculate is H as M. Such that the states in H as M satisfy the S square of psi is equal to H square S plus 1 of psi, and Sz of psi is equal to HM psi. So all of the states in this sub-Hilbert space must satisfy this reaction. So how do we do it? First step is write Hamiltonian, write basis of the Hamiltonian, and so choose the product basis. And the product basis is exactly what we saw here, or we write it every particle like kind of independent. Now, for example, in the spin 1/2 particle, we just wrote it here. Where is it? Here. Okay. This is the product basis we saw here. Afterwards, and then plus calculate the Hilbert space dimension. Dimension, which is just the number of states you have. Afterwards, so then for the 2 is find an explicit representation of a state Sm and determine. And now I'm telling you what I mean here. So here we can underline everything which is what we want and then what to do it. So the idea is that we use some properties of the lowering and of the ladder operators, and this is that the S plus of SF is equal 0, and S minus of S minus S is equal 0. So this is my M value, and this is my minus M value. Also the M value, which is minus M. And these we saw in the lecture, and also it follows from the representation of the 2 operators, which I put with a hat. And so what is the procedure? Start with a state with the highest or lowest M of the product basis. And therefore, we know that no superposition is needed. As it's unique. And now I'm telling you what I mean with it in the example. So this is with the highest or lowest of M of the product basis. So in the example, up is 1/2, 1/2. Up, down will give me, so this is the SM representation. And here is in the product basis. Here, this will give me 1/2 because it's been 1/2 and 0 because the total sum is 0. And here, I will have up and down and up, and this is the same. And here down and down, and this is 1/2 and minus 1/2. And these I put a tilde because these are not eigenstates of the S2 operators. So not eigenstates of S2 operator. So I could just say this is the M value of this state is 1. Oh, actually here is 1 and minus 1. Sorry, this is 1 and this minus 1 because we sum the two spins. So these are my values of M. And therefore, I take the lowest, for example. Why? Because I know that if I apply S minus to down, down, this will give me 0. If I apply S plus to up, up, this will give me 0. And if I look for a state with defined S and M, this follows that it must have an M, a total M, which is well defined. So I can only take superposition of the states with the same total M. And the only state with M minus 1 is the down, down. So this is, so down, down is a state of the SM form. Okay, is this concept clear? Same, we can conclude that up, up, so at the same time, this is equivalent to tell that up, out is a state of SM form. But we only need one for an SM space. And then we construct the other with laddering operators. So this is exactly the first step. To find one, this is given, start with a state with the highest or lowest M. And step 2 is, or this is actually step 3 now, calculate S. Because M, I know, okay? So here M is equal to 1. So yes, but I mean, okay, let's forget. So this is in the notation SM, we cannot write it like this because we don't know. So if we use really, when we use something like this, so let's put a tilde everywhere here. If we write something like SM this tells me this is an eigenstate of S2, only for eigenstate of S2. Okay, so here I was just telling, okay, what is the M? We can also make like this, maybe it's more clear, product basis, and then we write what is the M. And this is M, what is the eigenstate of a SQuID operator, and here this is the sum of my spin values, and this will be 1, this will be 0, this will be 0, and this will be -1. Of course, then any combination of these two states here will also have an M, which is 0. Exactly. Yeah. Does it answer your question? But these we cannot write in the SM procedure because they have to be an eigenstate of the S2. And of course, some of the combination alpha up down plus beta down up is an eigenstate, but we have to determine these alpha and beta, which are exactly the Clebsch-Gordon coefficients, because we see here, this would be your alpha and beta. Writing an SM state as a superposition of product basis states, which is exactly what you did, and this is alpha or beta depending on the state. Is that clear? Anything else? Great. Okay, I'll continue and then otherwise. So we exactly, yeah, for the down down or up up case, we know that we cannot make a superposition of them. So we know that these states are exactly an eigenstate of one of the HSM of the subspace HSM. Exactly this. Yeah, this is exactly the point, the main point of the calculation of the Clebsch-Gordon coefficients. And with this, we can also look at something else, because the idea is, yeah, calculate S. So we want to find out this value here. How do we do it? The idea is we know how S plus and S minus act. And we know that for S plus of SM is equal H square root of S plus 1 S minus M plus 1 of S and M plus 1. Okay, so we see that if we have one HSM, because we determine it here. So for example, for the spin 1/2 system, we have up or down. In the lecture, you use the down. If we have the down, we will apply the S plus, because it's a minimum M. So if we apply the S minus, it gives 0. If you do it wrong, you will see it straightforwardly, that it returns 0, so you have to apply the other operator. So what in the example of spin F, we know that, so down will be my 1/2 and -1. This is S and M. Will be an S, which we want to determine, and -1, which is M. So here, if we apply S plus, we will get the H bar of square root of S times S plus 1 minus M, which is -1. So -1 times 0 of S, and M plus 1 is 0. But we also know that the S plus operator will be a S plus on the first times the identity plus identity. So it acts exactly as the two separate. So what do we have? We will have that S plus of down, down will act as H bar S1 times S1 plus 1 minus M1. And these are the values of the first spin. And then if I take the down, down, this will raise my first spin and keep it the second low, like exactly like we saw before. And then exactly like here, S2, S2 plus 1 minus M2, M2 plus 1. And now here I did a bit of mess, but this is down, up. This down, up, the state we have here. So with S1, S2, SM1, and M2 known, because these are two single particles, two spin 1/2. They both point down, so they are two both spin 1/2. So we know that S1 and S2 are 1/2. They both point down, so we know that these are both minus 1/2. And if you calculate it, now we are not doing it, but you saw it in the lecture. So see lecture notes. I'm just replying it, but these and these must be equal, okay? Because we apply it just exactly on the same state. And here I forgot S plus of S and minus 1. If we equalize the two, so these two are equal, okay, then we will get, and this is where I don't write all of the calculation, but we just write the main result, which is exactly what we are looking for. This is H bar square root over 2 of up, down, plus down, up, divided by square root over 2. So this is important that we have. So here important is that we have a normalized state. Okay, and coefficients. So if here you find a sum over, for example, up, up plus down, down, divide it here by the coefficient such that you have here a normalized state, and multiply it the same coefficient, which you see I did it here, the square root over 2 and 1 over square root over 2. Why this? Because now we can make kind of a coefficient comparison. What is number, it's number. What is a state is a state. So we found two things in one. We see that S0 is equal 1 over square root of 2 of up, down, plus down, up. And we see that H square root of S plus 1 is equal H square root over 2. This means that S is equal 1. Is this step clear? Very important, your state has to be normalized. Every quantum state has norm 1. So these here, don't forget, otherwise you do everything wrong. So now we found first state of our, now I'm doing it smaller such that you can see it. We found a first Sm state by taking it the one with the lowest possible m. We found what is S of this state. And we also calculated the second state, which is great. In general, how we, now it's number 4, is calculate the rest of HS by applying the S plus operator. And you could also apply the S minus. If you took the state with the maximum m, then you have to lower and go down with the S minus. If you took the state with minimum m, then you go up and see which states are higher with the S plus operator. And this is like the sketch you saw in the lecture with the S and the m states, or if this is like something like this. So this is a fixed S, and these are all of the m's possible. This is another S, and these are all of the m possible. So this is just a calculation, and once you will get a 0, so you see, okay, I spanned my full Hilbert space. Or actually, if you know S is equal 1, this means m can be -1, 0, and 1, because it can be always between -s and s. So you have to find 3 states. Once you have them, you calculated your first HF. And afterwards, the challenge is going to another sub-Hilbert space. So what's point 5 is find an orthogonal state of this basis with minimum or also maximum, if you want, m. Now, what do I mean here? So example, for 2 spin 1 particle, spin 1/2 particle, if you calculate, and you did it in the lecture, you have these 3 states: up, down, plus, down, up, and up, up. So I cannot find a state with m equal -1, which is orthogonal to this basis, because the only possible state is down, down. So it's not orthogonal. Same for up, up. No chance to find a state orthogonal to it or to this basis with m equal 1. What's the only possibility is here, 1 over square root of 2 of up, down minus down, up. Yeah. Now, this case is a bit special because it's the simplest one, and this is actually the only state. And then we have 4 states, and we already span all of the Hilbert space. Agree? So we have 2 particles, each of them has a local dimension of the Hilbert space 2. So we have 2 to the 2. The basis has 4 elements. Otherwise, what do we have to do here? So repeat 4 and 3 and 4, and we will go back to what 3 and 4 until you span the full Hilbert. What is 3 and 4? If we have now this with a state with the minimum value possible of m, we then apply the rest of this space of the subspace applying S plus and S minus operators. Okay, and we calculate how this space is otherwise spanned, because we know that the S plus and S minus operators jump from one state to the other, from one eigenstate of S2 to the other, with the properties we also know. So we can also, yeah, actually we should also calculate the S. So yeah, okay, no, this is correct. Yeah, apply 3, we calculate S with the S plus and S operator, we calculate the rest of the states. And this was just that this is a 6 and we have to apply 3 to 5. So we jump exactly to, if we did this here, we jump to another S and we calculate all of them, we calculate S, and then we find a state which is orthogonal to the basis we found up to now and has minimal n or maximum, and we jump here. So in the lecture you did a slightly different cooking recipe. The idea is basically the same. It comes exactly to the same result, and you can follow both. The exercise sheet, anyway, exercise 3 is very guided, so it tells you here, for example, it doesn't ask you to find the orthogonal state and then you have to calculate all of the others. We give you the expression such that we are sure, you are sure that you are on the right point, and then you can go. And yeah, now this is the cooking recipe. It then allows you to calculate the subspaces. Now we will do in the last 2 minutes a comment. So why are we putting all of this effort to calculate some coefficients in a basis which we don't know exactly what we can do about? So why HS are so important? And by HS, I mean that the H total is a combination of subspaces with the same spin eigenvalue. Sorry, I'll just show so example is 2 spin 1/2 particles in a magnetic field. So, and we have that the magnetic interaction of these particles is given by H. So the Hamiltonian, I write it, oh, now I use the same H for Hamiltonian and Hilbert space, very bad. H magnetic interaction is given by a J, which is a constant and a real constant. And then S1 times S2, and now I will tell you exactly what these are. What is the S1 vector? This is the vector telling the Sx, Sy, Sz operator for particle 1. Okay, and S2 is exactly the same for particle 2. Of course, I can put here a 1, 1, 1, and 2 Sy, 2 Sz2. And this is a 2 and not a Z. This means that I will have a H magnetic, which is equal J Sx1 Sx2 plus S1 Sy2, and same for Z. Now, the eigenstates of this Hamiltonian, or ground, yeah, okay, so ground state of the Hamiltonian. And now, why am I telling you about the ground state? Because we learned a couple of weeks ago that the ground state is the state where the system finds. In nature, we find a system in the ground state where the energy is minimized. We have that for J is greater than 0 is the singlet. 1 over square root of 2 of up, down, minus down, up. And for J less than 0, we have the triplet. So we have 3 degenerated ground state, up, up, 1 over square root of 2 of up, down, plus down, up, and down, down. So this is all of the states. So we see that, first of all, our Hamiltonian, like the composition of the Hamiltonian we did in the lecture, is actually has some sense, or for different properties of the system, depending on the magnetic interaction, we are in another subspace of the eigenstate of the S2 operator, which have completely different properties. First of all, the S value, or here S is equal 1, and here it's S is equal 0. For example, if I calculate a state, which is an approximate form, it has a lot of numbers and we cannot discover it, we can calculate the expectation value of our S2 operator. And if we see that S is equal 0, we know that J is greater than 0. If we see that S is equal 1, we know that J is less than 0. So the physics, the real world physics decomposes actually our system in these sub-Hilbert spaces. And that's why we are looking at all of these adding spins. Great, this was a short motivation just to tell you, because I remember that when I learned these things, I was not very excited because it's just a lot of very simple algebra calculation, putting operators and finding out stuff which were very abstract to me, and I was not so passionate about. And with this, I wish you a good day. The lecture is at 1, okay, as you agreed with the other Lidia, and so that you can have lunch, maybe it's nice. And if you have any question about the exercise sheet, please write in the Moodle or write me an email also. And otherwise, have a nice week and see you in 1 or 2 weeks, depending on how we plan. Bye bye. And I'm still here for questions if you have.